Hi everyone. So in this video we'll discuss the issue of the complexity of the hypothesis space. What we mean by the hypothesis space is basically the model or the function that the model is trying to predict, right? So given observations, a series of observations, the model is trying to predict some function. This function is basically the hypothesis, right? And the space of hypotheses, that's what we call the hypothesis space, or all the possibilities of the hypotheses. So in this video, we will use some notation from some linear algebraic notation. So if we have a linear function in two variables, let's say x1 and x2, then this function can be represented as f equal w1 x1 plus w2 x2, right? So the function has two parameters, w1 and w2. And this function lies in a two-dimensional hypothesis space, meaning that if you look at w1 on the x-axis, w2 on the y-axis, then every point in that two-dimensional space represents one solution or one function that the model can predict, right? So why are we talking about dimensionality? Usually this dimensionality of the linear hypothesis space or the vector space representing the hypothesis space is a good measure of complexity, right? So it reflects on the computational time of training the model and on the capacity of the model or the capability of the model to predict a wide range of functions, right? So it reflects on two things. The time, this complexity, reflects on the computational time and on the accuracy or the performance of the model, right? So if f is quadratic, then we obtain, if f is quadratic in two variables, we obtain a set of solutions known as a conic, right? So basically it's the intersection of a hyperplane with a cone, right? So you get different shapes as we see in the figure. You can get a circle, ellipse, parabola, hyperbola, right? So you can get these different solutions through these are different functions that the model can represent, right? So here we will have a higher dimensional hypothesis space if f is quadratic. If f is cubic, we will have an even higher dimensional hypothesis space, right? So what's the trade-off? You get more complex functions, so the model can predict more complex things, so it can have lower accuracy with observations that are not as easily distinguishable, but it will require a larger training time, right? Now, one key point, we'll get back to this question of complexity and its implications throughout the course. But one key point out of this video, one takeaway lesson, is that the number of parameters, the number of free parameters, whether it's w1 and w2 in the case of a linear function here, or whatever free parameters you have to represent a quadratic function in two variables, that number of parameters is not necessarily the same as the dimensionality of the linear vector space that represents the hypothesis space. So let's take, for example, let's take an extreme example of what's known as radial basis function kernels, right? And ignore the word kernel for now. Kernel is just meaning a function that the model is trying to predict, right? We will come back to it later. But this is an extreme example because these functions are very powerful functions, the RBF kernels. And they're actually inspired by neuroscience, but that's something you can, that's not the main point here, but you can read about it. So they are very interesting functions in terms of their origins. And they are also kind of famous or known because they are known to be very powerful. But that comes at a cost. So let's see what this cost is. So an RBF function of a variable x, that variable could be a vector, right? Is basically the negative exponential of the L2 norm or the Euclidean distance between this vector x and the center point C. So here in a two-dimensional space, if x has x1 and x2, right? Then let's say x is this point here, and you have a center point C here. So basically it's the negative exponential of the Euclidean distance between x and c divided by sigma square. Sigma square is called the variance of the kernel, and this kernel is also known sometimes as a Gaussian kernel. Now it's called the kernel because it's like you put a kernel or a Gaussian around the center point C, and this Gaussian starts to fall around C, right? And when it hits x, that's the value of f of x, right? So the farther x is from C, the lower the value of f of x is, and the larger the value of the variance, the faster this kernel will fall around C. Okay? Now, so the value of f of x is defined by how far x is from the center C. Now, this function has only one parameter, which is the center point C, right? So even though this function has only one parameter C, it's actually infinite dimensional even if x was one dimension. So even if x lies on a single line, x is just a scalar value, this RBF function is infinite dimensional. Now let's see how that is true. So let's take a very simple example where sigma equal 1. So f of x, x is one dimensional, f of x equal e to the minus c minus x squared. Now this is equal e to the minus c squared times e to the minus x squared times e to the 2cx. Now if I decompose this e to this 2cx through a Taylor series expansion, I get an infinite sum. An infinite sum of 2 to the k over k factorial times c to the k times x to the k. Now, if I play with this whole equation, e to the minus c squared times e to the minus x squared times an infinite sum of 2 to the k over k factorial, c to the k, x to the k, I can represent f of x as the following, as an infinite sum of a part that depends only on c, which is square root 2 to the k over k factorial times c to the k times e to the minus c squared, times another part that depends only on x, which is the square root of 2 to the k over k factorial x to the k times e to the minus x squared. Now this is a rough explanation, so I'm not providing a rigorous proof for it, but you can think of these two terms as a dot product between two vectors that are infinite dimensional. So this part here, I can think of it as an infinite dimensional vector, right? Each element of that vector is basically square root 2 to the k over k factorial times x to the k times e to the minus x squared, and the k goes from 0 to infinity. So the first element of this vector is k equals 0, the second element is k equal 1, and so on, right? And these are coefficients of dimensions, right? Or so let's say, so for example here you have x1 and x2. These are bases for a two-dimensional space, right? So here I can think of these as coefficients for bases in an infinite dimensional vector space. And using the same basis but different coefficients, I have another vector in the infinite dimensional space, c to the k e to the minus c squared, and the same, k equals 0, k equal 1, and so on. So why is it that the RBF kernel is very powerful? It's actually the same reason why it's infinite dimensional and why actually training what's called as an RBF network, which has activation functions as the RBF functions, training them can be quite costly in terms of computation, because even though I'm choosing one parameter, which is the center point C, that actually corresponds to choosing a vector in an infinite dimensional space, and my point x gives me another vector in an infinite dimensional space, and the value of f is actually the dot product between these two vectors, right? So that's a view that that can give us an intuition, like thinking always as we go on, like about our model in terms of representing one hypothesis in a linear vector space, that and analyzing the dimensionality, or thinking in the back of our minds while we are designing our models about the dimensionality of that hypothesis space. That's a very useful representation to give us an idea of the computational cost of training that model, and also the accuracy of that model in representing functions that may not be straightforward to represent. Thank you.